Okay. So we're going to do this in two pieces. Hopefully we take somewhere around 2 hours. We'll be out by 8 p.m. Ish. That's the hope. So I'm going to do two sides. I'm going to teach about machine learning, kind of what is it at the high level. Then I'm going to show you machine learning, some examples of machine learning through Tensorflow, which is the tool we're going to use. And I'll talk about Tensorflow a little bit. And then once you've seen the actual examples, then I'm going to switch. I'll stop the recording, upload that one. Then I'm going to switch to this Windows machine, which doesn't have anything Python or TensorFlow or anything installed on it, and I'm going to take you through the process of getting TensorFlow onto the machine. And that could get interesting because I haven't put it on a Windows machine before, so we might run into all sorts of little hooks and stuff. But the punchline is you'll see where the points of resistance are in getting it set up on a machine, and I'm pretty sure we'll be able to get it on there. Okay, so second video will be setting up TensorFlow on your machine. What we're doing on there will work on a Mac as well, just I've already done it on the Mac. It'll be similar on there. Cool? Okay. All right, so let's talk about machine learning in general. So machine learning. Now, kind of the idea here, if you saw the message that came out from Professor Locklear earlier today, that was something I wrote up for him. But and if you had the programming classes with me, one of the things I teach in there is that the computer programming is hard for humans to get good at because we're so good at solving problems. And I usually bring up that thing on the first day of class, like how many of you walked to class today without bumping into any walls and stuff like that, right? Really, really hard thing to walk, yet it's not even worth our full attention, right? We're sitting there texting and stuff like that while we're going down the hall and we're bobbing and weaving in and out of people. We don't hit any walls, anything like that. So then I said, okay, well, how did you walk? How did you go about not bumping into any walls? I said, well, I just did. So maybe you look ahead, maybe you kind of steer a little bit, but you're not thinking about walking in terms of all the little muscles you have to flex and all these things. So walking, while we can all appreciate is a really, really complex problem, we can also appreciate the fact that we can't really tell other people how to do it. Okay, even if you're training, if you're a parent and you're trying to teach the baby how to walk, I guess. I haven't ever actually done this. I've been an observer. I've been an observer of teaching the baby how to walk. But you're almost just giving them hints on figuring it out themselves, right? Well, first of all, you can't articulate all those little muscle movements and things like that.
They wouldn't even understand that.
Huh?
They wouldn't even understand all those
Well, none of us do. We just know that we can do it. We know that we can catch our balance and keep ourselves from tipping over and stuff like that. Okay, so the punchline is that we all believe there's some pattern. There's some, there is a solution to walking, right? And there's a solution to a lot of other things that we can't necessarily explain. Because it's too intricate or something like that, and maybe not even worth our time thinking about all the little things. But that doesn't change the fact that at the underlying level, there actually is a pattern that translates to walking. All right, so my first experience with machine learning was maybe the year 2000, 1998, somewhere in that ballpark. And what we did is we created something called a neural network. So we're just going to say machine learning is training a neural network to, I'm going to say, find the pattern associated with a solution to a human solvable problem. All right. What's a neural network?
Well, the brain is a neural network of tasks.
Well, neural network as it relates to computer science is kind of what I'm getting at here. So we have this thing called a neural network. And this is an attempted model of the brain. And we're going to say very, very simplified. And I'll talk about what that means here in a few minutes. All right, but if we were drawing a picture kind of a neural network, we might have some inputs. And then we might have some outputs. Let me give these guys some color. All right, now to make this look all fancy, we'd usually have a bunch of lines here between all these guys, and I'm only going to start drawing them because it will take too long. So every input would be hooked up to every single one of these what are called hidden nodes. And all these boxes are something called neurons. We can think of them like that. All right, so then imagine that these other two boxes have the exact same connections to all of these guys, and each of these guys has arrows that go over to the green boxes over here. So this guy connects to every one of these. And then every single one of these yellow boxes will connect to every single one of these green boxes. Make sense? All right, so you get the point. I don't need to draw the rest of the lines. Okay, so this is what a neural network looks like. And what I'm saying is this is trying to model some, let's call it tiny aspect of the brain. Now the starting point here is that we don't really understand how the human brain works all that well. All right, so we're kind of having to make a guess. But we have created some proof that the human brain is able to come up with patterns to solve problems, because as human beings, we've seen ourselves do it for years and years and years and years. And now, through machine learning, we've seen computer models, neural networks, solve the same kind of problems. There are going to be some problems that we'll have to kind of find the right balance, and I'll talk about that in a little bit. But in general, it's able to solve some very interesting problems that maybe we didn't consider could be solved by a computer before. All right. So the idea here is that let's say that these inputs here might be zeros and ones. So we're going to give it a 3-bit number, 3-bit input. And that 3-bit input in each one of these lines then has some value associated with it, usually called a weight. All right. And we're not going to go into too much of the details of how neural networks actually work, but every one of these lines has a value. Okay. And this guy here is usually called the hidden layer. This is the hidden layer. All right, and we'll talk more about that in a minute as well. All right, and then again, these guys here each have values associated with them. And then these are our outputs. All right, so the idea here is that every single one of these guys is going to have a value between 0 and 1. That's kind of, we have like a normalized value, and I'll explain why that is. But it's going to give us a value between 0 and 1. Now, what we typically use neural networks for is for classifying data, okay, classifying things. So as an example, if somebody wants to handwrite some letters, something like that, all right? So we can take a picture of, like, let's say we draw the letter S, okay? And then we can take a picture of that. And then we make that picture grayscale. Take any color variations in the paper and stuff like that out. And then we turn that into a big binary string that is a representation of the representation of that picture. That makes sense? So we have this representation of this picture as a bunch of zeros and ones. Now, in our little example here, I'm pretending like it's only only 3 zeros and 1s. Okay, when in actuality it'd be a lot more than, than 3. But it's only 3 in our little example. Then what we're going to do is we're going to feed that information through this network. And we're basically we're going to, this 0 and 1 times this weight, and this 0 and 1 times this weight, and this 0 and 1 times this weight. And so all this math going through there, and then multiplied by all the numbers that come out of here times this weight, times this weight, times this weight, times this weight, over and over and over again. And in the end, it's going to spit out one of these. Let's just say we had 26 outputs for the 26 letters of the alphabet, something like that. Okay, so one of them is going to be the one that's closest to a 1. All right, that means that we have the most confidence in that output being a certain letter. So if I drew an S, okay, and we represented it as 3 bits for some strange reason, and we fed it through this whole thing, and this is an S, then an A, then a B, then a C, then a D. Randomly pick those letters because I can keep them straight. All right. This S would probably have a number of like a 0.7, 0.8, something like that would come out of there, where all these other ones would be lower numbers. Okay, so this network, after it was trained, this network would correctly, let's say, guess what an S looks like if it's given an image of an S. Well, given the data associated with an image of an S. Okay, but the reality is when we first established the neural network, and we give random weights to all these little these edges, the edges that go between the neurons, we're effectively guessing. When I feed it the data associated with that S through here, it's just doing some math and spitting out some numbers over here. Now I have to have a little cheat sheet on the other side. So maybe I know whether the thing that was just fed through was an S or not. Let's just assume the first time through it was an S. All right. And let's say this guy came out as a 0.2, this is a 0.7, 0.4, 0.5, 0.6. Clearly, it guessed wrong. Okay, it did not correctly guess the S based on my initial neural network. So what we do then is we update the network. So we go through and say, you got it wrong, slap it on the wrist, then go through and tweak the weights. So hopefully the next time through, it guesses a little bit closer, a little bit closer, a little bit closer. Okay, but that's just for S's. At the same time, the next time through, I might feed it an A. And it might guess the A wrong, so I'm going to update it. So what we're trying to do is we're trying to balance this network, get numbers in here across all of these things, that when I feed it data, either an S, an A, a B, a C, or a D, or an E. Did I get an E? S, A, B, C, D. All right, so when I feed it data that is from that set, over time, I can get all the numbers in this neural network balanced so that it gets a very high percentage of them right. It guesses right. Does that make sense? Okay, so then the idea would be, once I've taught it how to translate language like that, I should be able to give it new data that it's never seen before. Okay, I should be able to have somebody who wasn't part of my original handwriting group draw an S or draw an A or draw a B. I should be able to feed it into this network, and I should be able to get a good prediction of whether or not, of which letter it actually translated to. Does that make sense? Now, the more complex the network, potentially the better fit it might have. And you'll see when we do some training of networks today that sometimes we're only able to get to 60 or 70% accuracy on our training data. Now, that could mean a couple of things. That could mean that we need more training data. You know, we haven't been able to look at enough pieces of handwritten letters in order to truly get a network balanced out. It could also mean that our network is too simple. We need more inputs, or we need more hidden layers or something like that. It could mean both of those things. So it's kind of this big, cool experiment, which is, I think, a lot of fun. All right. Now, I was mentioning a few minutes ago my first experience with machine learning, and it kind of got me hooked years ago, 98, 99, something like that. Now, we all know how to do simple multiplication, right? You know, remember we're like, what, second grade or something when you learn the multiplications table, and you have like the little flashcards? They don't do flashcards anymore? Now you just use an app?
No, they just had big charts at the table.
Yeah. Oh, I had to make flashcards.
We do.
My mom helped me make flashcards. All right? So I made flashcards. And so somebody would quiz you, they'd hold it up, and they'd have the answer on the back side of it, and okay, like that. Okay, but here's the deal. So the 1 through 5s table, right? Now, when you're learning the 1 through 10s table, let's say, you ultimately kind of end up memorizing it, right? I mean, isn't that ultimately what happens?
Yeah.
Okay. Yeah, when I say 7 times 2, you say 14, you didn't really do math. You just kind of memorize that that's what it is, right?
Yeah.
There's some neural network in here that made all that work. So what we did is we wrote a neural network, something along these lines. We created an object-oriented neural network thing using what language we're using, probably C or C++, something like that. And we had all the data of the 1 through 5s table. So we represented each number as, I think it was a 8-bit binary input. So we would have a total of 16 inputs here for the two numbers we were multiplying together. So like a 1 times a 5 would be the 8-bit representation of a 1, followed by the 8-bit representation of a 5. So for 16 total inputs, and then we had some number of hidden neurons, and then we had our outputs, and this would fire to I think we did it as a 16-bit binary output to capture all the possible values we could have. Does that make sense? All right, so now that seems pretty random, doesn't it? I'm going to feed it 16 zeros and ones, multiply those zeros and ones by some random stuff, ultimately spit out 16 zeros and ones, convert those back to their decimal equivalent, and it's supposed to get the right math? That sounds far-fetched, doesn't it? Well, so what we did is we had a training set. All right, so let's kind of add that to our notes here. So we have something called a training set. Training set is a collection of inputs with expected output, effectively flashcards. Okay? Given these two inputs, given these 16 bits of input, this is the output you should get. All right? So that's our training set. Now, while we're creating this slide, let's just go ahead. I'm going to also create one that says test set. This is data similar to our training set, but it is data that the network has never seen. All right, with the idea being that you train the network with your training set, and then once you're convinced that it's reasonable, then you go back and you test the network with your test set, and it should shockingly get a bunch of them right. Okay? So what we did is we kind of made a guess, and this is the starting point for a neural network. We had to decide, well, okay, well, how are we going to represent our inputs? We decided, well, we're going to do them as two 8-bit values, so 16 total zeros and ones as my inputs. How many hidden nodes? We just rolled some dice. 20. You're just kind of making a guess, which is why this is kind of fascinating. You can just experiment with it and see how little changes make it better and worse and that kind of stuff. All right, then we decided that our output field we could represent, really you could have done it as just 8 bits, right? Because 10 times 10 is 100, right? And we could fit that inside of 8 bits. So we could have just done 8 bits as output. I don't remember what we actually did for our output, but whatever. So in any case, what we did is we had our training set was the 1 through 5s table. Every single one of the inputs, every single one of the outputs, and we went through maybe 50,000 times. So 50,000 times we fed it information. If it got it wrong, we slapped on the wrist, we updated the weights a little bit, fed it more information until it got a really high percentage of those right. So you're kind of thinking that this neural network, we're kind of balancing this guy. So we call this thing a model. Well, at least that's what Tensorflow, which we're talking about today, does. Calls this guy a model. So once we have it trained, once we have it balanced, it's almost like this black box where we can drop two numbers into it, in our example here, and it will drop a number out on the other end that should be those two numbers multiplied together. right? Because we trained it with thousands and thousands and thousands of iterations. So we trained our network with the 1 through 5s multiplication table. And I think we got it to 100% correct based on training it on the 1 through 5s table. It might have been like 97 or something, but because sometimes you'll get to a point where you have to stop training it because it'll never finish. You have to set some sort of threshold. You have to say, okay, well, I want to train this guy until it gets to 92% accurate, because I let it run for a week and it never got above 93% accurate, and then you're not, you're just kind of spinning your wheels. So you're going to take that model and say, I'm going to get it as accurate as I possibly can, given my initial guess at what this network should look like. All right, so we had this thing trained, like let's say 97% accurate. Then we fed it the 6 through 10s multiplication table. This is math it had never seen. And it got like 90% of them right. Isn't that kind of fascinating?
Yeah. For humans, it's not that easy.
Well, we memorized it as people, but we didn't necessarily think about it as a pattern, right? Yet we just trained this neural network thing on data that, well, we trained it on the 1 through 5s table, but tested it on the 6 through 10s table. And it did really, really, really well, which implies that there's actually an underlying pattern to multiplication. Yet we have trouble articulating what that pattern is. But now we kind of believe that maybe there is one. Make some sense? All right, so neural networks have been around for a long, long time. And back then, my buddies and I, we maybe created kind of our own little library for more conveniently creating neural networks, where we can say, okay, here's how many input nodes we have, here's how many hidden nodes we have, here's how many outputs, but we perceived that all of our data would always be zeros and ones. We didn't really necessarily work with the nature of that data. So even though for us, we were trying to make a neural network that was kind of malleable, that we could apply to a whole bunch of different kinds of problems, it really was only specific as far as what we understood about neural networks. All right. Well, now machine learning has kind of become a big buzzword. All right. It's popular. We're starting to apply machine learning to all sorts of things. If you watch the commercials for like IBM Watson, which is IBM's machine learning platform, I think one of the commercials has these elevator repairmen showing up to fix an elevator a week before it's supposed to break. Okay, because they've been capturing all this information about the elevator and how different, at what rate different parts wear out and things like that. So rather than waiting for it to go out of commission, they show up when Watson says the elevator is going to break down soon, you should go and service it. Something like that. Okay. Now, is that a real thing? Who knows? That might just be if they're what they did for their commercial. I don't know. I don't know the answer to that. But the bottom line is, just from what we just talked about here, it's at least plausible that if you had enough collected data, that there might actually be a measurable pattern between the amount of time since the last service and the number of starts and stops the elevator has done and all this other data that might exist, for them to actually make with high confidence a guess as to when this thing needs to be fixed to prevent maybe worse damage if you don't fix it in time. So now imagine applying that to more important problems. Okay, if an elevator goes out, it would be bad if like the cable snapped or something, but generally speaking, if the elevator's out of order, the consequences are people have to walk the stairs, right? Okay, but now you start applying it to, when does your car need to get fixed? You don't have a tire blown out. Airplane engines, all sorts of other things that might have worse consequences than walking a flight of stairs, okay? So machine learning, we're going to see over the next several years, is going to be, well, it's already being done now, but it's going to become very popular in the news, how it's applied to all sorts of problems we didn't consider. And hopefully this will get you started. What we deal with today is our crash course on it, and then what you do with in the boot camp kind of get your intellectual juices flowing, where you're thinking about, what could I use a neural network for? Now, writing your own neural network is all fun, okay? But if somebody's already solved a problem, why reinvent the wheel? Okay? And there's several different products out there for doing machine learning. The one we're going to look at here is something called Tensorflow. Okay, so TensorFlow. Now, a tensor is a multi-dimensional array of, I'm going to just say numbers for our example here. So this is Google's way of representing multi-layered data. So I mentioned a little bit ago, without going too much into that, but I said that in my buddy in my little implementation, we basically made the assumption that all of our data came from numbers, and we would just represent them as some number of bits for a binary number. So that works for number things, right? So after we did the multiplication tables 1 through 10, we decided, oh, let's test this on bigger numbers, and other things like that. And we got some cool results and things like that. But we are certainly limited, right? Some of the things we think about machine learning being used today for is like facial recognition, right? Where if you have a picture of somebody's face, and then you decide how can we represent somebody's face as data. Okay, is it a bunch of, well, ultimately it's going to be a bunch of zeros and ones, but how do we represent those zeros and ones? Is it, is it what's, how do you get face structure from it? You kind of feed it through different math formulas, and ultimately to get yourself some sort of value that almost gives a unique fingerprint of a person. All right, there's all sorts of different approaches to how we can take a picture of somebody and turn that into data that might work in a neural network, let's say. All right, because ultimately what it's doing is you're going to feed, a neural network. You have a whole database of pictures of people from all over the world, and you're going to feed it into this neural network for learning how to identify that this is a picture of Charlie, something like that, okay? And then if we show them a picture of me, it determines it's a picture of me and not a picture of Charlie, all right? Well, the more data you have, and the more multiple pictures you have of the same person, the better. If we just have one picture of Charlie with the ball cap on, okay, that's probably going to lead to a lot of false positives. But if we have 5,000 pictures of Charlie, over a 3 or 4 year period, wearing different kinds of clothes and in different kinds of settings and all this stuff, all of a sudden now we have a reasonable amount of data about Charlie, and we don't just have one face of Charlie. So now when we feed, if somebody catches something, takes a picture of somebody, says, who is this? We run it through our neural network, which has this giant database of people, and it's going to spit out on the other end one picture or one person's name. It says, we have the most confidence that it's this person. Now, the confidence might only be 52%. So it might not be real confident. But out of all the things they had there, the person looks closest to this one. All right, and that could be meaningful in certain situations. So thinking about things like that, you can kind of imagine that if you just sit there for a few minutes, once you've gotten, kind of a machine learning tool in your hands, you could start saying, oh, well, I wonder if I can classify this data, if I can classify this data or something else. All right, so we're going to be looking at TensorFlow as our power tool that allows us to think about problems that machine learning could be applied to without us having to actually create. Well, we still have to create the neural network, but we're heavily leveraging TensorFlow's library for creating the neural network. That makes some sense? Okay, so that's kind of the high-level view of what machine learning is, and TensorFlow is something that this is created by Google. So that's Google's machine learning platform. Okay, so getting some expertise in this is certainly going to help with maybe internships and certainly jobs over the next several years, I would think. Right now, we're kind of in the elbowing for space area of machine learning, where you have some of the big players. So you have Amazon Web Services has a machine learning, so AWS ML is their thing. Google has it, IBM has it. Then there's 5 or 6 other somewhat popular machine learning platforms from lesser known places. Microsoft Azure has their own machine learning platform. So at this point, you have several big companies that you've heard of coming out with platforms for doing machine learning, and you're going to have different companies adopting different versions of these technologies. So the idea is once you learn TensorFlow, because you're learning about neural networks, you should be able to take that knowledge and directly apply it to one of these other platforms and just do it their way. All right, but there's going to be more and more jobs dealing with machine learning moving forward. Okay, so what I'm going to do is I'm going to go over to TensorFlow's website, and I'm going to walk through, we're going to go through one example in a lot of detail, and then I'm going to kind of quickly go through a second example, just kind of showing you the different kinds of data we can use to classify. And then I'll show you the code that actually does it and how it works on here. Then we'll stop the recording and upload that, and I'll switch to the other machine and show you how to get TensorFlow installed in your machine. And ultimately what you're going to have for the hackathon, so on Wednesday we're going to release the teams for the hackathon so you guys can start thinking about classifying data and things like that. What I'm going to provide for the hackathon, hopefully, is a whole bunch of data sets for you to choose from, as well as some sample code that allows you to create multiple models and use them in conjunction with each other. Because what we're going to look at in here today is building a single model for doing something. But if we kind of think about human beings and kind of think about maybe from a TensorFlow perspective here with models, if an animal walked into this room, okay, or somebody brought an animal into this room, if just an animal walked in, we might be kind of scared depending on predatory, not predatory, that kind of stuff. Okay, but an animal walks into this room, we would have a fighting chance to identify it as a human, right? Okay, so if you go to the zoo and you see some animals and the animals there, you look at it and say, oh, that's a bear. Oh, that's a tiger. Okay, how did you determine it was a tiger?
Certain characteristics.
Okay, specifically what characteristics? If you see a tiger, how did you ultimately decide that's a tiger? What did you first have to decide?
Stripes.
Okay, well, there's lots of animals that have stripes.
Orange fur.
Okay, yeah, fewer animals that have orange fur, but there are other animals that have orange fur.
I can dye my dog with a stripe.
Well, don't we start at a high level and kind of whittle it down?
Yeah.
So we look at the animal, we say, okay, what kind of beast is this? Maybe we immediately rule out human, right? And we decide, okay, well, that maybe we have we have an initial model, a classifier that says this is a mammal. Okay, so now I've determined with high probability it's a mammal. So now I have another model that knows how to classify mammals. So given that it's a mammal, what kind of mammal is it? So maybe we break it down into kind of the larger subgroups of mammals. I'll keep it relatively simple here. So let's say that we determine it's a feline. It's a kind of cat. All right. So we pick it through the next model. This model knows how to classify mammals. So when I put the data of the image of the thing I just saw, when I put it through the second model, it says, you gave me some mammal. I determined with high probability this guy's a cat. Okay. So now I have another model for classifying cats. Okay. So I take that data, I drop it into that model for classifying cats, and ultimately it spits out, this is a tiger. Make sense? Now, why do you think we wouldn't have just one model that can classify anything?
Because many animals can share certain characteristics.
Well, that's certainly true. But also, when you think about it from a machine learning perspective, we talked about training the thing. Do you think if we have a model that assumes your input is some kind of mammal, that it could and produces an output of kind of the classification of type of mammal, do you think that's going to be easier to train to a high probability than animal to exactly which animal?
The first one will be easier.
A lot easier, because now you have a known type of input and a significantly smaller number of outputs. So now what we can do is we can start stringing models together. Okay, you have a life. Maybe if you don't even know if it's a life form, there's something in the middle of the room. Maybe right off the bat, your model determines whether this is living or not. Okay, if it's living, it goes to your next models for what kind of living thing, mammal, reptile, so on and so forth. If it's not living, then maybe we're classifying it as plant. No, plants are living. Maybe dishes, whatever. You can kind of create but you go from model to model to model till you finally whittle it down to something smaller. And that's kind of how our brains work, right? At least we perceive that's how they work. So inside of our brains, we have all these neurons, and they're linked to each other. And chances are these guys are all hooked to each other in very interesting ways, and we don't just have that one thing where we see anything and immediately classify it as its final approach. It's completely believable for us to say, okay, well, I see this table here, and even though I don't necessarily know I'm doing it, I probably start off by classifying at the higher level and then whittling it down until I can figure out exactly what this guy is, even though I'm not aware I'm doing it. Make sense? Okay, so what I'll provide you for the hackathon is some sample code that allows you to link multiple models together. So we're going to learn in here how to make a model given some data. Then I'm going to give you code that allows you to have multiple models linked together to make decisions. All right? So let's go over here to this guy. So we're going to start off with this thing called basic classification. All right, and what we're starting off with here, so this is the data set they use for this thing, and we'll see how it trains in a minute. But this is pictures of a whole bunch of different clothing. So we have pants and sweaters and shoes and boots and stuff, a whole bunch of different clothes. I think there's 9 different categories. All right, so the idea here is this is our training data. So we take each of these pictures, and I'll show you how to get these. This fashion data set contains 70,000 grayscale images that are in 10 different categories. So images show individual articles of clothing at low resolution, 28 by 28 pixels. All right, so this isn't a high resolution picture, but it's the idea is that if you see a pair of pants, you could identify it as a pair of pants as a human, right? We look at it and say, that looks like pants. All right? So our hope here is that we're going to train a neural network that can identify clothing by an image of that clothing to one of those 10 categories. All right? So our data set's going to look like this. All right? Now we're going to have to do some stuff to the data to make it look make it work for our neural network. Like I mentioned earlier, if I'm doing the multiplications table, maybe we decide that we're going to have each of our numbers being represented as an 8-bit number, something like that. Okay, well, if we're dealing with pixels, if it's a 28 by 28 pixel thing, that's 28 times 28, so that's 784 total pixels that make up each of these pictures. And maybe those pixels have, other colors and things like that, so we might need to get as much noise out of our data as possible. So we kind of have to pre-process our data. All right, so we have all these pictures. And as a human being, if we looked at any individual one of these pictures, most of us could do a pretty good job of identifying whether that's a shirt or whether that's a shoe or whether that's pants, that kind of stuff, right? Doesn't seem like a real difficult thing for humans to solve. But if I asked you to write a computer program, based on what you know about computer programming right now, if I asked you to write a computer program that took in an image and classified it as either pants or a shirt or a shoe or something like that, that would be pretty difficult. Because now you have to figure out, well, what does it mean for something to be pants? You could kind of sort of explain it to somebody else, but even then it's only at a high level, right? So that's where a neural network comes in, where we can train it on the pattern of pants, even though we maybe have trouble articulating that. All right, so that's what our data set looks like. Now this is all being done in Python code, so I'm going to show it to you in pieces here, then I'll show you the actual running code that I broke into individual little chunks. All right, so we're going to be doing this in Python. So very first thing we do here is we create a variable. This is called the fashion minist whatever. And we're using a high-level API called Keras. Okay, and Keras makes doing TensorFlow stuff significantly easier than if we didn't use it. So it's kind of a power tool that allows us to make some of the neural network building components much easier. All right. There's actually another tool that makes it even higher level, because now they have a JavaScript library for TensorFlow where you can actually do all of it visually on a web page, but that's not any fun. Okay, so we're going to use Keras. Keras has a whole bunch of data sets built into it for kind of practicing using TensorFlow and stuff, so I'll probably give you a list of all the data sets that are in there. One of the data sets is called fashion. Okay? Now these are all variables we're setting. So we have train images, train labels, test images, test labels. So from what we've talked about before, these two things are going to be used for training our neural network. So we're going to have a whole bunch of images that we're going to send into the neural network. And then we're going to have the same number of labels that is our expected output. So if I feed it a picture of pants, from bucket 0 of train images, bucket 0 of train labels should say pants. Make sense? That should allow me to categorize it. All right. Then here's my next set of things, my test images and my test labels. So after I've trained that network up, the next step should be that I should be able to go and test my trained network and see how well it does on data it's never seen, data I didn't use to train it. So if I test it on the same data I trained it with, it's going to do just as well as it did when I trained it, right? So if you show it completely brand new data, then you have some confidence that, oh, I made something. This wasn't just a fluke. It didn't just get really good at the data I trained it on. It actually can identify similar data with similar accuracy. All right? So over here, this is our data set. We're telling it to load data, and what it does is it returns 4 pieces of information. So these are 4 arrays for our intents and purposes. So an array of images, an array of labels, another array of images, another array of labels. Okay? And then when you run this in TensorFlow from the terminal, and we'll see that here in a few minutes, you're going to see it downloading crap off the internet. All right? This is coming from the Keras library. All right, now that label thing actually is going to hold just numbers. So bucket 0 of images might be, if we can see it here, I don't even know what that is. Is that like a dress? I think it's a dress. Okay, bucket 0 of images is going to be a dress. Then the label for that would be a 3. Because dresses are associated with a label of 3. Okay? So a lot of the times we want the data to be numeric data, and if it isn't currently numeric data, we're going to convert it into numeric data, and you'll see here in a minute how we can clean this data up a little bit. All right, so after these first 2 lines of code, this is going to be inside of a Python program. If you were to run that program, it's going to do all this stuff and download these data sets. Now, this line of code, this load data, it knows to check local cache to see if you've previously downloaded it. So only the very first time you run the program will it actually go and grab a whole bunch of data. After that, you don't even have to be online to get it. It knows it's cached. Okay? So you only ever see this part once per machine you run it on, so don't freak out if you don't see it downloading every single time. All right. Now we might put into our code, here's like a little Python array that just says, bucket 0 is a t-shirt top, bucket 1 is trousers, bucket 2 is pullover, bucket 3 is dress. We're going to use this for doing our mapping because our labels are going to be 0 through 9. I need an array that says, oh, well, if the label was a 0, it actually referred to this kind of thing. If the label was a 3, as we just looked at, that's actually a dress, right? Because the neural network's going to like to work with numbers. We're going to want to ultimately convert our output into the word. That way when we see that the output was a 7, we don't have to go and look up and what was a 7. We can write the code to convert it to the word of what it just recognized. All right, so just creating a little Python array here. Now they're saying if you want to write some Python code to explore what the data is, kind of proving that you were able to read it in, you can look at the shape of the training images. So this is downloaded. Remember our array of images, an array of labels, another array of images, another array of labels. So if I ask those training images to tell us its shape and I were to print that out, it's going to say there are 60,000 images and they're 28 by 28. Okay? So Keras has built into it the ability to take a whole bunch of pictures and turn it into data that we can actually work with. We don't have to solve that problem as a person who's leveraging TensorFlow to do machine learning. All right? We have to solve a little bit of an extra problem, but right now we have numbers that we can work with. All right? Similarly, if we look at the labels, it's going to say there's 60,000 labels. So this is just a whole bunch of individual numbers. All right, here's our array of labels. So notice it's just a big list of numbers between 0 and 9. Test images. So we have 10,000 images to test after we've trained it with those 60,000 images. Also 28 by 28. They're making things fairly simple here. So you imagine if you trained your array or trained your neural network on a whole bunch of 28 by 28 pixel images, and then you take a picture with your iPhone of a piece of clothing that is, 15 megapixel or something like that, full color, all this stuff, that might not get detected all that well in your network. I'm training it on data that looks a certain way, and it might get very good at detecting data that looks very similar. But if I start changing the size of something or changing the equipment it was captured with, things get a lot more sketched. So you can imagine that machine learning, it's really exciting from the possibilities perspective, but it actually could be somewhat frustrating when you try to actually solve a problem that you think would be cool to solve, and you can't quite come up with the neural network or the right shape of, as they use the term, shape of the data to make it work. All right, so you got to keep manipulating your data or make a bigger or smaller neural network, stuff like that. All right, so this is just showing what the output would be. So it's proving that we've gotten those 4 different sets. 2 sets of images, 2 sets of labels, and how big each one is. All right, we're not actually going to write that code, but this is actually Python code that we could print out, and it'll show us that stuff. Okay, so then here's that set where I said we can pre-process the data. So for example, if I want to look at my 0th training image. So for my training data, I want to look at bucket 0, and this is a thing that allows you to plot. I'll show you in code what the actual library. This is a math plotter that we renamed to PLT. All right, so I'm going to create a figure. I'm going to feed it an image. I don't know what color bar does, but it looks like it probably just gives it everything some shade of greenish. All right, so it makes it a little bit more, you can differentiate between what's very dark and what's not so very dark without having all the colors of the rainbow. But ultimately, if we plot that, it's going to show us something like this. Now, as a human being, if you look at that, what do you think you're looking at? A shoe type thing, right? Could be a boot, could be I don't know what else, it's like a weird slipper or something, but it's a footwear. That is footwear.
Looks like a Nike.
It's a Nike swoosh. So that's our Nike swoosh. Okay. But punchline is, as a human being, we can look at that and we have just classified that as some kind of footwear, right? But even right now, we're not exactly sure what kind of footwear. Maybe it's a basketball shoe, maybe it's a boot. Could be either one of those would be plausible right now, right? Okay. So that's kind of the point here. We're going to train a network that's going to do better at classifying something that looks like this than we are. Now, if we looked at a much, much, much better quality picture, we might have a better shot at picking this guy out, right? Give us some full color, a little bit higher resolution, maybe give us some context, like somebody wearing it, performing actions. If we see somebody at the free throw line shooting hoops, basketball shoe. If we see them on the ski slopes, ski boot, something like that. All right, but this is proving that we got our data in here to our code, and we can display it if we're interested in displaying it. None of this has to do with the neural network yet. All we've done at this point is read in our training data, read in our testing data, and now we're just proving that we got that. And here's some examples of the size of it and what some of the images might look like. All right. Now, it's talking about pre-processing the data. It says the data must be pre-processed before training the network. If you inspect the first image in the training set, you will see that the pixel values fall in the range of 0 to 255. Okay, so this is like a color. So notice how it's plotted this here up to 255 here. So what they're suggesting we do is we scale these values to a range of 0 to 1. Remember earlier I mentioned that the outputs would be between 0 and 1. We kind of normalize the data. Okay, so we scale these values to a range of 0 to 1 before we feed them to the neural network, before we put them as inputs into the neural network. So for this, we cast the data type of the image components from an integer to a float and divide by 255. So we could take our training images. So this is a collection of our tensor data that we read in. And we're going to take those same training images and we're going to divide each of those values by 255.0, which will give us some number between 0 and 1 as a floating point value, right? So we just translated the numbers down to a range, a floating point range. And this, part of this was trial and error from the past, but it also kind of makes sense as if we're trying to ultimately classify stuff based on the confidence that we have and how close it is to something else. We might say, okay, well, if something comes out as a 0.9, I kind of look at that as like 90%. That's pretty confident, right? So 0 to 1 tends to be kind of what we work with in terms of percentages. So maybe it made some sense to try that, and it turned out that networks train very well under those kind of conditions. All right, so we'll update our images, and we'll update both of our images to be pixel values between 0 and 1 instead of values between 0 and 255. Cool. So we just done a little math doctoring. All right, well then they went through, and this is still not neural network stuff. They just said we're going to display the first 25 images just to prove that we have them. All right, so it's just going through here, and it's showing the image. Okay, so that first guy we looked at here, he's actually it's an ankle boot. It's an ankle boot is what that is. All right, so it shows the images as well as the label underneath it, so we can kind of get a feel for what these things are. Because when we feed this to the neural network, we're going to feed it a numeric input for this picture, and we're going to expect whatever the ankle boot number was, 9 or something like that, as the output. If we don't get that output, then we're going to update our network with some new values. Okay, so this is just showing what those first 25 things are. Ooh, that's a sandal. Sandals are like used for the sand, right? You don't want heels like that on the sand. Am I looking at that? That's like a high heel, isn't it?
Mm-hmm. This is the one next to it.
Yeah. Those are sandals? All right. Fair enough. Okay. Yeah, see, these look more like sandals. Okay. So, showing us some of those things. But now we get down to the more neural network part of this. Building the model. Okay, so remember, a model is going to be kind of a little decision maker, a classifier, something like that. All right, so we're going to create a model. We're going to ask Keras to give us a sequential model. So the basic building block of a neural network is the layer. Layers extract representations from the data fed into them, and hopefully those representations are more meaningful for the problem at hand. Most of deep learning, how many of you have heard the phrase deep learning before? Okay. Do you know what deep learning is relative to machine learning? It's actually fairly simple. Deep learning means that we have more than one hidden layer. We have a deeper neural network, more than one hidden layer. And the implication there is that if we have more than one hidden layer here, that means we have more neurons connected to each other, so kind of a scarier web of interconnected neurons and edges. Well, actually, it's neurons and synapses. Okay, so a scarier collection of those. And the perception is we should be able to solve more complicated problems. Again, it's still guesswork, right? We're still guessing, well, do I have 2 hidden layers or do I have 30 hidden layers? How complex do I make this? At what point? Because we're going to talk in a little bit about something called overfitting, where you actually train something too good, where it becomes so good at the training data that it actually now has trouble with generic data you didn't train it on. So it really is all this experiment. Okay. So we're going to use Keras's built-in, this is kind of our default model, the sequential model. And we're going to, first, we're going to have 3 layers in here. All right. So we have our input layer, our hidden layer, output layer. Okay, so this pretty much matches up to the picture I drew back here. Input, hidden, output. So our input layer is going to be, we have this function that's part of Keras called flatten. We use this for We use it mostly for images, but we use it from other things as well. So we say, well, here's the input shape. So we have images that are 28 by 28 pixels big, right? So this guy is basically saying that's what our images look like, 28 by 28. Now, when we say we're going to flatten those, when we think about a picture, we think about it as being this 28 by 28 square. Flattening it means we're going to make it a big, long stream of numbers. It's flat, one line, instead of 28 lines of 28. Make sense? So what was that, 700 and some odd? 28 times 28, 784. So 784 numbers right next to each other as like an input array. That make sense? All right, so what that ultimately is going to translate into here then is for my inputs here, I have 3, but the actual inputs for this thing is going to be 784. In fact, it might even be bigger than that because it's going to represent them as tensors, so it might actually map those numbers into their binary equivalents.
1024.
Not necessarily because the values they're going to hold is between 0 to 1, right? So it'll be a value. So actually, it's going to be 784 inputs. It won't do it as binary because we have decimal values or floating point values that we can multiply by the weights. So this guy implies that we're going to have 784 inputs. But the point is, using Keras and using TensorFlow, we didn't have to specify how big our inputs are. We just had to say our data is our images of this size. Go ahead and flatten the data because that's the appropriate thing to do for TensorFlow, and make the correct number of inputs based on what my data looks like. Okay? So I have highlighted there, that says I'm building a neural network, I'm building a model. Okay, so my neural network's going to have this many inputs, whatever that comes out to be. Then I'm going to create a density layer of 128 hidden nodes. That means 128 of these guys. So imagine that I didn't even want to spend the time drawing all my little arrows here. If I had 784 red boxes, and what was this? 128 yellow boxes, and I had to draw 784 lines to each of those yellow boxes from each of my red boxes. It would be actually 128 lines from each of my 784 boxes. So 784 times 128. So over 100,000 lines, 100,000 synapses between input and hidden layer. Okay, and then my output layer has 10. Why do you think it's 10? We let it figure out how big our input layer is based on what our images look like. We then, let's just say, randomly picked a hidden layer of 128. Just like, let's give them a nice smart center core there, just kind of pulling a number out of this guy. But this 10 means something specific. Why did we choose 10 for our output?
So maybe 10 to 100% chance.
How many of those are there? 10 of them. So we are looking for this model to be a classifier. Okay, so we want this guy to spit out, it's going to spit out 10 outputs, but one of those 10 outputs is going to be the highest value. It's going to say, this is what we think it is with the most confidence. Make sense? Because we had 20 or something, and now all of a sudden, how do we fit 20 into our 10 options? All right, so it's gonna give us 10 total outputs. It's not just like one of those fires. Like if you think about building like a circuit or something with electricity, it's not like just one light comes on. They're all going to have a number that comes out of them. Okay, but those numbers can then be analyzed to see, which of these 10 is the highest? Whichever one is the highest is the one that it had the most confidence in. Make sense? Go ahead.
Is it like a stack where you're like pushing each of the images on each one of those?
Pushing the image onto each one of those.
Like if you're gonna sort all of the images.
Are you talking about the flattening part here at the beginning?
No, I understand what that is. So like you have those 10 categories,
Yeah.
and if you wanted to like essentially sort your set,
Oh, yeah, it's not. I think I get what you're saying. So once it's trained, you can maybe do something like that. But during the training process, you're going to get a number, and so we're going to have, let's just say number 3 was the biggest number, and we say, okay, so this classifier for that input, or this model for that input thinks it's number 3. Let's say it's actually supposed to be number 5. That says, oh, we got it wrong. So now we're going to go back and update those weights on all those synapses so that the next time that same input comes in, it hopefully gets a little closer to the right answer. Keeping in mind that the next guy coming in might now be a little bit more off than it would have been a second ago before I changed those weights. So that's also kind of a science too. We're relying with the algorithm under the hood here is something called backpropagation. And we're relying on TensorFlow's approach to that to update the weights enough to make a difference next time, but not too much to break other ones we used to get correct. Okay? And what we're going to do is keep feeding it our inputs over and over and over and over again in order, tweaking it till it gets a high percentage of them right. Once you then have a trained model, then you could use, if you wanted to sort your data, then you could drop your images through and sort them in individual buckets because we're not checking for correctness of the buckets. We're assuming the model is already classifying it accurately, or as accurately as it's going to be able to. All right, so input is dictated by the nature of our data, but we're letting TensorFlow make those decisions for us. Okay, we're just saying, hey, it's good to have flat data. Here's the size of our images. Go ahead and flatten it for us. Whatever input size that should be, just do it. Make that layer for us. Great. Okay, next layer, I'm not sure why they picked 128, but let's just say they did for a good reason. Could have just been a coin flip or 128 coin flips or random number generator, who knows. All right, typically you do use a power of 2 for the number of hidden layers, hidden nodes, but I'm not sure from the research of backpropagation whether that actually is meaningful. Like would 127 actually work less well than 128? I don't know. I don't know the answer to that. But the output here, that's going to have to deal with our the nature of what we're looking for an output. We're having this model be a classifier of between 1 of 10 things. Therefore, we have 10 outputs. All right. If we were classifying 2 things, okay. For those of you, do any of you watch? I asked this in one of my other classes. Do any of you watch Silicon Valley? One person watches Silicon Valley, so she'll get this joke. So in Silicon Valley, they have one of the guys in the show makes an app that is supposed to be like for foodies, where you can identify, it was kind of sold as you take a picture of something and it tells you exactly what kind of food it is, right? But that's not really what it did. It did whether something was a hot dog or not a hot dog. That's what it actually classified. Like, did you take a picture of something? Is what you just took a picture of a hot dog, or is it not a hot dog? Something else. So in that particular model, we'd only have 2 outputs. Hot dog or not hot dog. Make sense? All right, so I was able to get the joke in there somehow, but now is that a not interested in Silicon Valley thing, or is that we don't have access to HBO?
I don't watch TV at all.
Oh,
Mostly just watch
now we're getting into the Amish category.
I mostly just watch on the internet. I don't have HBO. I don't know.
Yeah. Well, if you ever get a chance to watch Silicon Valley, you can binge it at a night pretty easily. It's like 8 episodes per season, but it's very computer sciencey. It's about startup companies and writing software and finding bugs and getting capital funding and stuff like that. Okay, so here's us describing the model. Okay, so what we've done at this point with that code I have highlighted is we've said I want to build something that looks like this. Okay, we haven't trained it yet. I just have the model sitting there. All right. All right, so then we're going to compile this model. So this next thing says we're going to compile the model. And I don't know what the Atom optimizer is, but one of their functions for compiling it. I also don't know what this loss function is, but here's our thing. So loss function measures how accurate the model is during training. We want to minimize this function to steer the model in the right direction. So again, this is like those variables that we can turn on and turn off as we're training a model. And really that function has to do more with how big our moves are when we update the weights. All right, so built into TensorFlow is some kind of known to be good under certain conditions built-in models. All right. Optimizer, this is how the model is updated based on the data it sees and its loss function. So this loss function then drives this optimizer for when it goes through and it tries to get this model to get closer and closer and closer to perfection across all your training data. Okay, metrics used to monitor the training and the testing steps. The following example uses accuracy, the fraction of the image that are correctly classified. Okay, well that makes some sense, right? That's the only one out of those that makes complete sense to me. So that's the idea is that, look, if you expected a shoe and it said it's a shoe, it's a shoe. We're good. Okay, you don't need to make any changes. All right, so we're doing this based on accuracy. All right, so up here we are describing our model. Now we are compiling our model, which will actually produce the actual model. So now we have all the nodes generated, all the stuff. It's ready to go. Ready to start being trained. All right. So now is where we train the model, and it's called fitting. All right. So we're taking this model that we just described, and we're trying to fit it to the data. All right, to our training data. And that means that we're going to be updating little weights in there and stuff like that until it ultimately will accept all the inputs from our training data. Okay? Or accept a high probability of them, or a high number of them, rather. All right. So here's the line of code for that. We're going to take our compiled model, so model.fit. What are we fitting it to? We're fitting it to these inputs. That's our training images. These desired outputs. And then we're doing this across 5 epochs. So it's going to go through all that stuff 5 times. So that's 60,000 images, 5 total times. Make sense? And between each of those 60,000 images, every individual image, we're going to be adjusting those weights just a little bit depending on whether they got right or wrong. Now you could make the argument, well, what if we do more than 5? What if we do 50? Well, it'll take longer to train. At that point, maybe it gets a little bit better. Maybe it actually gets a little bit worse. But you might then start getting into the situation where you get overfitting. Okay, where you get really good at classifying your training data, but you've actually gotten worse at classifying data you didn't train it with. So again, it's like trial and error, which makes it kind of fun, right? It's like you're working with this puzzle. All right. So as an example, as we go through this, here's our 5 epochs. It's going through here. Let me scroll over here. So the very first time through, it got 82% of them right. Okay, that was just on the initial guessing with updates along the way. So very early on, it probably was not getting a very high percentage of them right. But after maybe got through the first 1,000 or 1,500 images, it probably started zeroing in on some sort of better guessing. All right, so by the end of 60,000, they got 82% right. Next time through, 86% right. We improved a little bit. 87, 88, 89. So if we had run it through 7 epochs, maybe this 89 would have become 90 or 91 or something like that, or maybe it would have stuck at 89. Who knows? Okay, that's ultimately going to go back to nature of our data, how big the data set is, and what our neural network looks like, and also how fittable is our data. You know, at this point, we're kind of making a guess at what a neural network can classify and what it can't. All right, so when we're done training, we now have a neural network that gets it gets 89% of our training data right. Okay? So, at the end of that, I don't know why they said 88% because it was 89, but whatever. All right, so it's got a high percentage of it correct. Now we're going to see, well, how well does this work on data? Now we're going to test our model. We trained it. We think it's good. Now we're going to test our model. And so we're going to call our model, have it evaluate our test images and our test labels. And that's going to give us our test loss and our test accuracy. And we're going to print those guys out. So here we have a test accuracy of 87%. So it did a little bit worse on our test data than it did on the training data, but that's pretty good. This goes back to, up here, what did I do based on what I said earlier is I trained my neural network on the 1 through 5s table back from my first experience with machine learning. Then what did I do down here? I tested it on the 6 through 10s table, and it got a lot of them right. Make sense? All right, so this is it testing on data it had never seen before. All right, so then from that point forward, now we might say we have some confidence. We have a model that does a pretty good job. We can decide whether we think 88, 89% is good enough or not. If you don't think it's good enough for the job you're trying to solve, you can go back and tweak it, make a bigger network, give it more data to train on, train it longer, all sorts of stuff. Okay, but for us, we're going to say we think this is okay. 88's good. All right, especially when we were having trouble identifying what kind of shoe that was, and they have made up high heels for the sand. So, so whatever.
I don't see who wear high heels in the sand, 'cause it seems kind of
No, these people do. It's a fashion thing. Remember, it is a fashion. So actually, when I say that, I actually believe it probably does exist. Probably does exist. Okay. So then from that point forward, if we wanted to then test an individual image, so let's say now we have an app, okay? And in this app, we're able to take exactly 28 by 28 size, low resolution pictures, for example. I can then predict, based on the picture I just took, what kind of garment it is, what kind of item it is. Okay, so when I make a prediction, notice here's the output. All right, so this is our 10 outputs. So this shows our output layer. And as you look at this, it's kind of hard to look at data this way because with the scientific notation, you can't necessarily look at the magnitude over here to see which number is actually the biggest. So let's just let them cheat. So now we do the argmax. So what is the largest value out of these? It was number 9. So that's actually this guy right here. He was the largest value that came out of there. So the model's most confident in that image being an ankle boot or class name 9. Make sense? All right, so then they print some stuff out here. So here's like an ankle boot with 68% probability. So if you look at the outputs here, this is 0.68 is that actual output. That was the best it did. It said, look, out of all these inputs, I'm 68% sure that's an ankle boot. But that was the highest value I had compared to any of the other ones. So that's this model's guess for that boot. When I actually ran this data, this might have been on an older version of TensorFlow, or maybe it was an older version of the data set. I actually got a better. I think it was 100% certain that this was an ankle boot. And I'll show you that in a second here. All right, so it can print some stuff out, and so then this is just using the plotter to show some stuff. This really has nothing to do with TensorFlow in general. This is more just letting us as the humans see what did the image look like and where were the classifiers. So this is 7, 8, and 9. It's pretty sure this guy's a 9. It was only sort of sure-ish on an 8, a little bit-ish on a 7, but all the other ones were almost not plottable or something like that. All right, and you see this one is a little bit different. All right, and then they're just going through multiples of these and letting it go ahead and classify. So this was 68%. I think, did they show us a bad one? That's unfortunate. But in any case, you can get false positives, right? Obviously, we have a model that we only trained up to 89%. So over 10% of our guesses are likely going to be wrong. So maybe that's okay. Maybe they're close enough. Maybe instead of it being an ankle boot, it got a sandal. Still in the footwear category, but you hope you don't get a whole lot of dresses when you're actually looking at a shoe. All right. So that's kind of the high level. Well, not high level. This is the medium level version of how TensorFlow works. Now, what I'm going to do is I'm going to show you two different code things, because what they've done here is they show you here's training it, here's testing it. Now, the reality is after if you're writing an application or some fashion app or something like that you want to be good at classifying pictures of clothes, chances are you don't want to have to retrain your network every single time you launch it, right? Because the reality is that what's a trained network? A trained network is a collection of how many input nodes, how many hidden nodes, how many output nodes, and what are the values of each of these synapses in between. So once we've trained it, and we've kind of gotten it balanced just to as good as we're going to get it, then we can store how many inputs, how many hidden layers, how many outputs, and what the value of each of those synapses is. That's just storing a whole bunch of numbers. Once we have those numbers, we can actually recreate the neural network really quickly, right? Because we're not having to feed it data anymore. We're just building our model, compiling our model, updating the weights with the data we've already found out work. Make some sense? All right, so what I'm going to show you here is, let me do it on, here's the train close. All right, so the idea here is what I've added to the code is what if you want to save your model so that you can use it again later? You know, like I trained it on my closed data set today. Now I want to have an app that could just load that model and use it for future things. All right, so this is kind of the whole program for training it. So we import TensorFlow. We import this OS thing that allows us to do a file path stuff for where we want to save our network stuff. All right, and then here is Keras, that high-level power tool that we use for TensorFlow to make life easier for us. I don't know what we're using NumPy for, but whatever.
What is NumPy?
That's a good question. It's not a TensorFlow thing. It must be another Python library. Here. Let's Python NumPy. Fundamental package for scientific computing with Python. So n-dimensional array stuff, mathy stuff. So it's a library that does a bunch of mathy stuff. So maybe actually TensorFlow must be reliant on it. It's not part of TensorFlow, but TensorFlow uses the NumPy libraries to do its mathy crazy stuff. All right, so this is just me saying this is where I want to save my, my neural network data. And here's the directory where it'll be. So I'm asking the operating system to get me the path to this directory name where this guy lives, so I can write that data out. All right, so here's me getting my callback for my saving my model. So we're using Keras callbacks, model checkpoint. So as we go through and we train our model, I don't know, I think this happens probably after each epoch, it will write the current weights associated with your model for you to use later. I'll show you how to reload it here in a second. All right, so we're going to store our model checkpoint at this place. We're only going to save the weights, because we said that you only need the weights to reconstruct a thing, right? Actually, it's a little more than that. We're only saving the weights so that we will still have to remember what our model looks like, what the inputs are, hidden layers, stuff like that. We can actually make it store everything so we can recreate our entire model from our saved data. But the reality is the thing that takes the time is the training, updating those weights. So I don't know why the example didn't store everything, but you'll see how I use it here in a second. All right, so we're going to keep all the weights at this place, and every single time it finishes an epoch, it's going to call this function associated with our model checkpoint. So here's our data set. You've already seen this stuff before. Here's us taking it to 0 to 1. Here's us defining the model. Here's us compiling the model. Here's us fitting the model. Notice this last thing, though, in fitting, I've added this thing that says callbacks. So this is going to call that thing. So at the end of each epoch, it's going to save it to disk, the current weights, so that I can load it later if I want to. All right. So that's the training side of this. So I'm going to go ahead and I'm going to run this. So I'm going to do Python 3 And this guy is train. Oh, I need to go back one level, sorry. Where am I? There you go. Python 3, train, close. All right, so this is, it already downloaded the data. That's why you didn't see it downloading the images again, but now it's going through my various epochs and training the data. He got to 87.45. Now, actually, just out of curiosity here real quick, I'm going to come into the code here, and I'm going to change epochs to 10. Let's just see if it does better with more epochs, or if we kind of get stuck in that rut. So now it's going to go through all 67 or 60,000 10 total times. Yeah, see that last one actually got a little worse. 87.67. All right, 88. Yeah. Improved a little bit, but now we're at risk that it possibly just overfit. You know, we might have gotten too good at classifying our training data, and now maybe we don't do as well classifying test data. All right, so let's look at our testing thing. So I have this thing in here called, I think this is basic PY. All right, so this outputs some, this is that math plot thing, the PLT. All right, so I'm telling it where it can find my weights. I have this little function here that will allow me to plot an image if I want to use that. I don't remember if I left it as being used now or not. So this is just drawing stuff. It's not neural network stuff. So just ignore those functions for right now. So I actually don't even need, well, I will need the data set because I get my test images. So here's my data set. Here's me getting those 4 things, even though I'm not going to use the training things in here because I've already trained. I am going to use the test things. Here's my array of classifications. Here's me normalizing it. Here's me defining my model. Here's me compiling my model. But now instead of fitting it, notice I'm loading my weights from that checkpoint path. So that's me bringing in an already trained model back into existence. Okay? Then I'm going to evaluate my test images and my test labels. And I'm going to have it print out information about test accuracy and that stuff. And then it's going to do some stuff where it's going to show the first, what do I do, first 20 images or something. All right, so I'll come out here, and we're going to go ahead and we're going to run this guy. So this is Python 3, basic PY. So this guy's going to load my previously saved model. Let's see how it does. So I got 88% of those guys right. It doesn't have a scroll thing. It's too big for the screen, but you know, what you can see is what you can see. Just deal with it. All right, so it sees that 99% accuracy, 74% shirt. So all these it got right. I don't know if they had some wrong ones down there, but you know, this is kind of a code example of it loading stuff and getting stuff back. Which this? That's, yeah, so this is like the 99% accurate for the ankle boot was number 9. So that number was a 0.99. All these other ones were almost a 0. So this is a plot of our 10 outputs. So notice here for this one, we had 74% for shirt. So it came out with a little bit of certainty on 0, a little bit on 1, well, a little bit on 2 probably. And then whatever this one is, 7 or something.
Wait, the trousers 100%, why is it on the left side of the thing?
Because the trousers must have been a 1.
Oh.
That was a classification for trousers. Yeah, trousers were bucket 1.
Oh.
All right. So that's just an example of, I mean, this output is just us plotting the results of our neural network. This isn't TensorFlow itself. This is just saying, TensorFlow gave me a bunch of data, and I can look at the data in terms of numbers, or I can go ahead and have it draw me some pretty graphs and stuff. Easier to visualize it, but this doesn't change the way whether we got it right or wrong. Okay, so just for the sake of time, let me just tell you really quickly what the other one I was going to show is. Pretty much the same model. Did we follow this reasonably well for what this did? I'll put all the code examples up. But what the other one did is instead of it being pictures, it reads in text from Internet Movie Database. So it brings in user reviews for movies. And there's 25,000 reviews. And what it does is it tries to classify as a review as either being a good review or a bad review, a positive or a negative review. Okay? So, you know, so now it's taking, you know, it's throwing out words. It's looking for patterns in reviews that indicate whether this person is speaking kindly about a movie or negatively about a movie. Make some sense? So just kind of an idea of working with different data, but from our perspective, it's kind of the same thing. Build a model, compile the model, fit it, blah, blah, blah. Okay, so let me go ahead and let me stop this video, start it uploading, switch to that machine, and then I'll show you how to install TensorFlow.